So LPC800 is the latest device that we've brought to market. So we think it's a great part, and we think it's going to be very well suited to the 8-bit space. So over this next 40 minutes, a couple of my colleagues, Paul and Amish, will go into some more technical detail who can, explain exactly why it's a good fit. So the LPC800, if you take nothing else away from this presentation today, if you can take these few points, then I'll be very pleased. So the first thing, we designed it to be really simple and easy to use. So we know that 8-bit is kind of simple and easy to use, so we've designed the 800 to be the same. High performance at a reasonable price point. So we want to give you more performance, better capabilities, but we know you're up against you have development costs, and we want to keep the same price point. So we've done that. We're giving you 2 to 10x the performance of 8 and 16-bit parts, and Paul and Amish will cover some benchmarking material that we can prove that to you. 2 to 3x power savings. So again, we'll show you, we don't just want to state these things, we want to give you the details behind it. Smaller code footprint compared to 8 and 16-bit micros. Single cycle I/O access, and we've included some new smart peripherals on the devices to try and differentiate ourselves against your current 8-bit parts. So it's easy for us to say, yeah, this is a great part and it's going to replace 8-bit, but that would just be stating something. But we actually, as NXP, have current 8-bit customers using 8051 based micros. So we spoke to them and we asked them, right, if we're going to come with a 32-bit part to market, what do we need to do to get you to design in with it? So the first thing that they told us was it had to be very easy to use, simple, didn't want anything too complicated. They wanted upside in performance. They were getting to a stage where they were introducing graphical interfaces or a more complex user interface, so they needed more performance. They still wanted to keep the power efficiency. A lot of the applications were battery operated, so we need to keep the low power. Wanted longevity of supply, so we have that. And all at an 8-bit price point. So took all this information and we developed the LPC800. So the 800 is building on our current portfolio of the LPC1100. So there's over 100 parts based on the Cortex M0 core. But we're now using the Cortex M0 Plus core on the LPC800. We have a difference in performance. We're positioning them differently in the portfolio. The 1100 series will run up to 50 megahertz. The 800 will stop at about 30 megahertz. And you can see the flash sizes and the pin count. So we're in the 16K flash range and up to 20 pins. The roadmap we have for the portfolio, so this is the first device, the LPC81X. We have samples in all packages available today. We've got example code, and Paul and Amish will cover some of that. But we will go into production towards the end of this month. So the parts are real, they're available. This is what it actually looks like. So at the core, you have your M0 Plus. We've got up to 18 GPIO. One of the cool peripherals that we have on there is the switch matrix, which allows you to route any function onto any pin, and that's absolutely any function to any pin, so there's no restrictions, apart from power and ground obviously, but they're the same in every package. We've got a whole host of serial connectivity, 3 UARTs, I2C SPI. We've got the State Configurable Timer, which can do all of your input capture, output compare, PWM generation, as well as just standard timers. We've got the multi-rate timer, which again gives you more options and can create some interrupts. And then a comparator, up to 16K of flash and 4K of RAM. So on the simplicity side, what we've done to try and keep things simple is we've included drivers in the ROM. So it's saving you on application code space, and basically these are API calls that you can do to configure the peripherals. We've also got small page program array size, so you could potentially use some of the flash as E² PROM, so saving system cost. Power efficiency, we're under 100 microamps per megahertz, and we've got various different low power modes that can be called as an API call as well. So it is a Cortex M part, so we are leveraging the ecosystem as it stands today. We have forums that you can access. We have our own engineer-to-engineer site, LPCware, and basically all of the hardware and software debuggers available, standard in the market, we support them. So I mentioned all about the 8-bit price point, so starting from 39 cents, the different options, even in DIP 8 packages, so for simple prototype and manufacturing, but up to 20-pin TSOPs and different configurations of memory. So we see it in different types of applications. You know, we have the 1100 that cover some of the higher end on the garage door opener type applications, but we see the 800 coming into things like fire alarms and some basic stuff, LED toggling, switching, some of that air freshener type application space. So low cost, low performance type applications. So with that, hand over to Paul.
Okay, so let's talk about the simplicity and flexibility of the LPC800 family. Okay, so start with clocks. Very flexible clocking structure, as you can see. We have an internal RC oscillator, 12 megahertz plus or minus 1%. That's the standard clock, so when it boots up, that's where it's running from the internal RC oscillator. And then you have a watchdog oscillator for low-powered operation, so you can run it off the watchdog oscillator. You have a main oscillator, that's for the crystal, and so you can feed in a crystal from 1 megahertz to 25 megahertz. You also have a clock in as well, and you have a PLL in there if you want to multiply the clock source. And then you also have a low-power oscillator, which you can use to wake it up from a power-down mode. So that's a very low power, running at about 10 kilohertz. And it wakes up from a deep power down mode. So a lot of flexibility in the clocking of this device. Code density, when we compare it to 8 16-bit parts, I mean, of course, you know, this is a 32-bit part, but you got to remember most of the instructions, almost all the instructions are 16 bits. As opposed to, let's say, for an example, C51, where it's an 8-bit part, but you know, the instructions can be anywhere from 1 to 4 bytes. So even though it's an 8-bit, it takes a lot more code space than you first would envisage for that. So, and also if you have to go beyond the 64 kbyte address space of an 8-bit part, then you're going to run into paging situations and things like that, which take extra code space. So although it's not intuitive, you can actually get better code density with this 32-bit part. Here's an example, and this is an extreme case. So you take a look at Cortex M0 Plus, which can do a single cycle multiply, 32-bit multiply. And this is a 16 by 16 multiply. It takes 1 clock cycle and 2 bytes. And if you look at a C51 in contrast, it takes 48 bytes and 48 instruction cycles, and however long that is, depending upon which ADC51 core you have. So again, when you run into this sort of situation, you can certainly get much better code density with a 32-bit part than an 8-bit or 16-bit part. One of the features that we've added to it that Stephen touched on was called the switch matrix. So that allows you to map these a peripheral to any port pin that you want to, with the exception of VCC and ground. So if you wanted, let's say, put UART to port 0.2, you can just tell the switch matrix to do that, or you can do the 0.3. So when you're laying out your PCB and you decide, oh, it'd be easier to change those around, it's just a matter of changing a few bits in your code and you can map it to whatever pins you want. So very, very easy to move these functions. Okay, so what we do have is a PinMux tool. So in this PinMux tool, so it comes up and you choose what part you want. It's very simple to use. Let's say I want to use a UART, the USART. Choose it here, and I can just say I want to use U1 TXD here, and I want to use U1 RTS or RXD right there. So you just can map it, and it's a nice little visual tool. You can use any of the USARTs, SPIs. So it's an easy way to map it, and again, it shows you right there what pin is assigned to the particular function. And after you're done with it, after you've mapped your various pins, you can actually get your code, and there's your code. So it actually creates a little code. So again, a little bit of complexity, but we've made it easy to do this. So basically this code, all it's doing is mapping those two pins. You have to enable the system AHB clock control. That's all done for you. Because each peripheral, by the way, has its own clock, right? So the switch matrix has its own clock. The I2C block has its own clock. So in order to use the switch matrix, you have to turn on the clock. So that's the first section in there, and then it's just assigning the various pins using the SWM pin enable function. So it's all done for you. You don't even have to think about it. Just done visually. Put this in your code, and it should work. Again, so that's one of the more complex things, and it's taken care of for you. And then one thing you can do is, because you do have the clock there, you can disable the clock after you're done. Save a few nanoamps of current, so because you don't need to clock the switch matrix anymore. So it's always a good idea to turn off any peripherals that you're not using. Okay. So any questions on the switch matrix? Pretty straightforward, especially with the tool. The I/Os, so very flexible I/O structures in these parts. And the big difference, if you're familiar with the Cortex M0 or M3 or the Cortex M parts, they took multiple clock cycles to access an I/O port. So one of the really prerequisites when we were coming up with the Cortex M0 Plus was single cycle access to all I/O ports, which it's pretty common in the 8-bit world, 16-bit world, which was not common in the Cortex M's before this. So now we've added this single cycle access, so now you can toggle a pin at the same speed as your clock, core clock. So that's a big advantage of the Cortex M0 Plus core. Let's see, enhanced bit manipulation, so you can access these things on a bit level, byte level, word level. So, very flexible there. It has programmable pull-up, pull-down resistors. It has pseudo open drain on a lot of the pins. It's got inverter functions and repeater modes, so a lot of enhancements in the I/O structure. You can use up to eight of the GPIO as interrupts. Any of the GPIO you can use as interrupts. And again, you can use as edge sensitive, level sensitive, rising edge, falling edge. So very flexible interrupt structures as well on the GPIO pins. They have glitch filters on them, programmable glitch filters, and so you can select how many clock cycles of a filter that you want to use. High current drives on 4 of the pins, so up to 20 milliamps in that. And then we have 2 true open drain. Now normally they're used for I2C, but they also, since they support Fast Mode Plus has high drive capability. So those pins also have the ability to sink a lot of current. So they're true open drain and they have high drive capability. So here's a scope tray showing the core is being clocked at 30 megahertz, which is the maximum core speed. And you can see that it's at every clock cycle, we're having a transition on the port. So we have actually a 15 megahertz toggling of the port pin. So very nice enhancement for the people who are used to the capabilities in the 8-bit parts. Okay, so as far as development tools, what we have is the LPC Expresso boards. And here's an actual LPC Expresso board that you see in the slide. And on the right side is the debugger. And that's what we call the LPC link. So all on one board we have a debugger on one side, and that's a high-speed USB interface. And then on the left side we have the LPC800. And we have a few peripherals on it, like we have a crystal on it, we have the part on it, obviously we have an RGB LED on it and a potentiometer. So a few things, but you also have headers and you can actually put it into a baseboard. We actually have some baseboards you can plug them into as well, so you can start developing pretty quickly using these boards. For these, we suggest using LPC Expresso. LPC Expresso is a free IDE, up to 128 kbytes. So that'll cover all these Cortex M0, M0 Plus types of devices. So that's a free IDE. But if you prefer Kyle and IR, that's perfectly fine. We support those tools as well. And you can connect your JTAG or your SWD to the header on the board, and you can bypass this debugger on the board and use your Kyle U-Link and the J-Link from IR. So very, very flexible. And they're very inexpensive. So let's just see how difficult it is to create a project. I mean, again, that's always the thing that scares people when going from an 8-bit to a 32-bit. And it's actually pretty simple to get started. So here we'll show the LPC Expresso IDE. And I've already set up the workspace. So basically it's on the desktop. Okay. So again, this is a free download. When you get it, make sure you activate it. So this one you can see it's fully activated, so you get the full 128 kbytes of code. Okay, so first thing you always do is you want to import the core parts of the project, and the core parts are the SIMSYS. Everything is based. We use SIMSYS compliant code, which is what everyone uses for their ARM-based parts. So we'll use the SIMSYS library. Okay, and this is starting from scratch. You could start with any of these other projects as well, but this one we're going to do totally from scratch. Okay, so here we have that, and we're going to do a new project. We're going to do it on the LPC800. I'm going to call it my first project, if I spelled it right. Okay. And this is going to link to this SIMSYS core library. And we're going to finish. Okay, so here's what our project looks like. It's pretty straightforward. So, thing you're all probably familiar with is a startup file. So that's given to you, right? Your startup file is something that you generally don't have to change, and that's automatically added to the project. So this has all the initialization. But what it also has, if you look on here, it has the name of all the interrupt vectors. So with the Cortex stuff, your vectors, your interrupts are just function names. So if you want to write an interrupt handler, this is the name of it, and you can just use it in your code. So that's in there. The only other, generally speaking, don't have to use this, change anything in this code. You just use it as is. You'll probably look up what the interrupt names are to find them. And then within this, it actually calls the system init. Okay, the system init file sets up all the clocks for you. Okay, so now that's probably the most complex part of it, but we've made that pretty easy too. And then from there it just jumps to main. Okay, so within the SimSys library, okay, what we have is the system, and this has all the clock initialization. And again, this is probably the most difficult thing when you're starting a new part, trying to get it initialized. You don't really have to change any of the code. It's all in these defined statements. Okay, so how do you get all these defined statements? Well, we make it pretty easy again. So what you can do is, okay, we have these little spreadsheets you can download from our LPCware site. So all our microcontrollers have these little spreadsheets. So let's say I want to run this part at, for some reason, 18 megahertz. Okay, well, it's at 12 we're going to use the 12 megahertz internal clock. 18 megahertz is not a good multiple of that, so I'm going to run this at 36 megahertz, and I'm going to divide it by 2, and that's going to give me my 18 megahertz. Okay, it's all done for you right here. Anything in the orange or brown, whatever that is not valid to use. So anything in the yellow, you can choose, 18 or 12. And again, what this does is it's going to put all this in these spreadsheets, which you can just put in that system file that we just spoke about. Okay, so we set the PLL. Now we need to do is set up the clocks. Okay, so here's the first part you start at. Okay, what do we want to do for the system PLL clock select? Or you actually, since we're going to use the PLL in this situation, right? We want to use the internal RC oscillator, right? So the system PLL clock select, right? It's already set up for the IRC. But here you have the various choices, the crystal oscillator or the clock in. We're going to use the IRC. Okay, so now we're at this point. So we've already set the PLL. Okay, so now where's the main clock coming from, right? So we can choose IRC oscillator directly, to 12 megahertz. We can take the input to the PLL. We can take the watchdog oscillator, but we're going to take the PLL out, right? Because we're going to take that 18 megahertz out of the PLL. So the main clock select, I want to use, as you can see, it's IRC, PLL, watchdog. I'm going to use the PLL out. Okay? Now the clock out select is just if you want to output the clock onto a pin to see if you want to see the actual clock frequency, and you can measure it or use it for other purposes. But we're not going to be using that. So again, all this stuff is done for you in a spreadsheet. So now you just have to take these values. So sys PLL clock control, right? So we go into CL clock, and instead of 41, it's 42. Again, we don't have to do a lot of thinking. Right here, the clock, divider, we have to remember to divide by 2, right? Because it's the 18 divided by, or 36 divided by 2. We want to, the PLL clock select should be 0. And now it's set for 1, so we need to set that to 0. And the main clock select should be 3, right? Because we're taking it from the PLL out. Which one was that? It was 0, right? Yeah. Main clock PLL 3. Okay. So now we basically set up the whole initialization of this. So now we need to go to main. So what we have on this board is we have some RGB LEDs. So all I want to do is blink an RGB. Actually, I'm just going to do the red and blue LED. Now the main was already, the LPC Expresso gave us the basic structure. I'm going to get rid of all these comments out of here. I don't need any of this. Okay, so my first function I like to call is the system core clock update function. Okay, so that that allows me to find the system core clock frequency, which is really nice to have when you're running timers, right? Because that way you can just feed that number into your timer functions. Next, what we need to do is initialize the GPIO. The GPIO at reset are all inputs. So what we want to do is we want to say LPC GPIO port. And then nice thing is it brings up these different registers. So the direction register is input output. That's all there is. Okay? So I just choose the direction and I want to OR it. Okay, and the red LED is port 0.7. So I'm just going to, and the blue LED 0.16. Now I want to turn one of them off at startup so that they're blinking on and off. So I'm just going to use the same sort of function. LPCGo port. And I'm going to set it. The nice thing about the set function is it only affects the pin that you're setting. So in this case, I just want to set one of the pins. So I just say 0.7 now is high. Okay, so now I have two LEDs, or 2 port pins that are output, and one of them's high, one of them's low. Okay, so now I need some kind of timer. So what I'm going to do is the Cortex M family has a thing called the SysTick. SysTick is generally used for operating systems, things like that, but it's a great general purpose timer too, and really, really easy to use. So SysTick, what's it called? SysTick config, yeah. Config. And here's the nice thing, we can do system core clock, right? And I want it for half a second. There, half a second core clock. So that's going to interrupt every half a second. Okay, so that sets up the main loop. Pretty straightforward. Now I need to set up a SysTick interrupt, right? And where do we find that? We find that in the startup file. We can find out what the names of these interrupt functions are. And here's the SysTick function. So here we know. Okay, it's just a function name, so I just copy and paste into my main. And all I'm going to do is say LPC GPIO port. And this has got a really nice feature in it called not. And it's just going to toggle whatever that value of those port pins are. So I'm just going to toggle bit 7 and 16. Okay, is that going to work, Amish?
Yeah, so you change the system.
Where?
Get rid of that too.
Oh, yeah. System.
On bit 7, you got banks that work.
Oh.
Shift over.
Yep, see it? Should have worn my glasses. Anything? Okay, so fairly straightforward so far, right? Hopefully. So again, we just take one of these LPC Espresso boards, USB port. Of course, it's not going to work. It's a demo, right? Okay, so all I can hit is hit the debug, and hopefully we don't get any errors. And okay, so it found the debugger. Okay, so here you can step through this if you want. Okay, so you can step over it. Here you can see that, you know, as I step through it, you can see now that the two LEDs are on. I know it's the red one's a little hard to see, but I can put a breakpoint in. I can just run this puppy. Right, so I just every time I hit a breakpoint, so I take this one out, and we just keep running it. So here we have a Blinky. Pretty quickly, and obviously you need to learn little bits of the language, but once you know one Cortex part, they're fairly similar, right? All the core, all your interrupts and everything are all the same. That's the nice thing about the ARM architecture. So that gives you, again, just to show simplicity and how a few simple tools can get you up and running quickly. Okay, so I'm going to hand this over to Amish, and he's going to be talking about the power.
Okay, so now everyone's kind of got the opportunity to see how simple it is to get a project up and running, how you can get the user switch matrix, code density. Now I'm going to kind of go over the power consumption, and you'll get a good feel of not only the power consumption but also the performance you get out of the LPC800, the peripherals. You'll see how easy it is to use and how flexible it is, and how you can use these features to meet your 8-bit application requirements, and you can also further enhance your 8-bit application with the LPC800. So the first thing I wanted to kind of cover is that Paul mentioned about the instruction cycles it takes. It's a lot less on the M0 Plus. So what's the end effect of that? So the advantage is that since it takes less cycles to execute a task, what you could do with the Cortex M0 Plus or the LPC800 is that you can actually run it at a very slow frequency to meet a performance requirement. So if you look on the top curve here, you'll see that there's a performance requirement that needs to be met. And if you compare the Cortex M0 Plus against the 8 and 16-bit processors, what you'll see is that the M0 Plus can run at a slow frequency, right? So it's right over here. And then you'll see that the 16 and 8-bit processors have to actually run at a little bit faster frequency. So what that means is, since the 8 and 16-bit processors are running faster, what's going to end up happening is you're going to see that the current consumption for those processors is going to go up as compared to the M0 Plus. The next slide, what I want to show here is that the flexibility you have with all the low power modes on the LPC800. So to start off, Stephen mentioned that in active mode, using a while one loop, it's about less than 100 microamps per megahertz. So now if you want to further reduce your power consumption, the first mode that you can probably go into and still have your peripherals running is sleep mode. So what happens in sleep mode is your clock to your core is gated off, but your peripherals can be still running. The advantage here is, of course, that in sleep mode, you can have your peripherals generate interrupts. You can still have GPIO interrupts. And also, the key point with sleep mode is that your SRAM and register state is preserved, so they're not lost. The current consumption that you see, the lowest power consumption that you can get with sleep mode is 600 microamps. And if you were to wake up from sleep mode, it takes about 2.6 microseconds. Now, as you look at this table, what you'll see is as you go deeper and deeper into the low power modes, the current consumption will go down, but your wake up time will obviously increase. So what happens in deep sleep mode is that the internal clocks are shut off. However, the flash memory is in standby mode. It's not completely turned off. So the advantage of having the flash in standby mode is that you can wake up a lot faster as compared to the power down mode, where in power down mode the flash is completely turned off. But with power down mode, your current consumption is going to be much lower as compared to deep sleep. So you can see that it's 1.8 microamps in power down mode versus 170 microamps in deep sleep mode. But again, the advantage you see here is, it depends on your application requirement. You see the flexibility you get depending upon whether you want a faster wake-up time or if you want lower power consumption. You have these options. Now again, in power down and deep sleep, both of these modes, your internal SRAM and register states are preserved, so they're not lost. The lowest power mode is deep power down mode, and you can get a current consumption of 220 nanoamps, but your wake-up time is obviously going to be a lot higher. And the reason being for that is because the chip actually goes through a reset when it wakes up. With deep sleep and power down mode, what happens is wherever you left off before you go into deep sleep and power down mode, you're going to resume back your execution. And in terms of interrupts for deep power down mode, you have two interrupt sources. Basically, you have a wake-up pin, or we have a new feature which is called the self wake-up timer. So you can basically, I'll talk about that. Basically, you can program the self wake-up timer to a certain count value, and once the count value is finished, it's going to wake up the chip on its own. So you don't need an external source to wake up the chip from deep power down mode. Also with deep power down mode, the internal SRAM and register states are lost, but we have provided four general purpose registers where you can actually store critical data for retention purposes. Another feature I want to highlight, this is a common feature that we have on a lot of our Cortex-based microcontrollers, and it's called power profiles. What power profiles are, these are basically API calls, and they are basically, they're part of our boot ROM. And the advantage with the power profiles is that it allows you to optimize your LPC800 power consumption and performance. So it depends if you want like a higher CPU throughput, you want more data processing capability, versus if you want low current mode, very low current consumption, then you can use the power profiles. The good thing about power profiles is that these are simple API calls. You don't have to go into the registers and configure the registers. You can just make these simple API calls. The end result is that you have less code to write, which translates into less code space. What we've done to demonstrate power profiles, we've used a benchmark called CoreMark. I'm not sure how many are familiar with CoreMark. I'll talk about what that is, but it's basically a benchmark that we use to evaluate our CPU processor. So with CoreMark, what we've done is that we've evaluated the power profiles, and with power profiles, we have four modes. We have the default mode, which is not using power profiles. Then we have the CPU performance mode, which is basically what happens in this mode is when you put the chip in CPU performance mode, your CPU throughput is going to actually is going to increase. So you're going to see a 30% increase in performance if you were to configure the LPC800 in this mode. You also have the option of, if you're not interested in, if you don't need CPU performance, then you can actually put the chip in low current mode, and the end effect of that is that you're going to see a 30% reduction in power. We also have an efficiency mode as well, and this is a mode that is kind of like, it's a balance between the performance mode and power consumption. One thing to note is that with the three modes, the CPU performance, low current mode, and CPU efficiency mode, all of these modes take less current consumption when you compare it to the default mode. So in summary, here's a table that actually shows these modes working when CoreMark is used as a benchmark. And what you'll see is that when you look at the current consumption, and I'm hoping to hear a question on this, by the way. Oops. So what you'll see is that the default mode, the current consumption is 2.5 milliamps. In performance mode and efficiency mode, the current is about the same. It is the same. And then in low current mode, the current consumption goes down to 1.56 milliamps. So that's current consumption. What does that mean with respect to CoreMark? With performance mode, you'll see that when you compare it to the default mode, you'll see that the CoreMark score is a lot higher. Higher the score, better the performance of the chip. And I'll talk about that, what that means. So you see that in performance mode, your CoreMark score is higher. In efficiency mode, it's the same. And the reason why it's the same is because this chip is actually It operates up to 30 megahertz maximum. So you're not going to see a significant difference. You won't see a significant difference between these two modes. But if you were to go to our future generation chips, which runs at 50 megahertz, you'll see another wait state added, and as a result, the performance mode is actually, the efficiency mode is actually going to be, the CoreMark score is going to be a little bit lower. And then we have the low current mode, and obviously the CoreMark score is a lot lower. Another key feature that we have on this chip is that we have ROM chip drivers. So we have the standard, if you're familiar with our LPC products, we have the in-system programming and in-application programming APIs, and these are APIs that are used for erasing and programming your flash. And then we also have a new feature called a USART and I2C API routines. So what's the advantage of this? The advantage is that, again, it's simplicity. So we want our users to be able to make simple API calls to send and receive data, whether using the I2C or using the USART. You don't have to go and go to the registers and start writing all these send and receive. You can just make these API calls. So simple, and the end result is, again, it takes up less code space. And then we talked about power profiles as well. And also another key feature with the power profiles is that you can actually configure your POL automatically. So if you have a desired frequency, you just make an API call for your POL, and that's it, it's done for you. So you don't even have to actually use the POL calculator. So another option out there, you can actually use the POL API calls as well. So with regards to performance, again, now CoreMark. So what is CoreMark? CoreMark is a benchmark that's it's provided by EEMBC. Basically, what it is it's an ANSI C code, and it consists of what it's supposed to do is it evaluates the CPU processor, and what it does, it runs like matrix manipulation. It does linked list operations. It does CRC calculations. So it's just working with the core and seeing how well the core can actually execute a task in a certain amount of time. And what we've seen is when we did a comparison with the LPC800 versus the Atmel 8-bit 8MEGA644 and the microchip and MSP430, what you'll see is that the CoreMark score is a lot higher when you compare to these chips. So as an example, if you look at the CoreMark score of 49.24 for the LPC800, what that means is that to execute a certain CoreMark task, it can execute it 49.24 iterations per second, as compared to, look how long it takes for the Atmel microchip and MSP430. Way too slow. So if you have an application that requires high performance, then this is definitely the chip you want to use. Now I'll talk about a little bit about the peripherals. Stephen touched on some of the peripherals in the block diagram. We have the MRT. What this is basically it's a timer with 4 independent channels. There's no output from the channels, but what can happen is all these basically the timer it's a 31-bit timer, and each of these channels has its own 31-bit value, so they can run independently. And each of these channels can generate a repeated interrupt, or it can also do a one-shot interrupt mode. Repeated interrupts, so you can have a repeated interrupts in your application, or if you want a one-shot, which is basically one interrupt, and you can kind of use that like as a software delay in your application. We talked about the self-wake-up timer. Basically, this is a 32-bit timer that can be used as a countdown sequence. And what happens is, once you enable this self-wake-up timer, you can use it to wake up from your low power modes. So again, you don't need some external circuit to wake up your chip. From deep power down mode, you can use a self-wake-up timer. You guys are probably familiar, I'm sure, with the windowed watchdog timer. We talked about the SysTick timer. And then one of the things I want to highlight is we have a new feature. It's a new peripheral. It's called the State Configurable Timer. In short, it's known as SCT. This is basically a general purpose timer. It does all the stuff that a general purpose timer does. It can generate PWM outputs, but it does a lot more than what a standard timer can do on an 8-bit microcontroller. And what it is before I go into the details, everybody knows a basic timer. You know, you do a count up and down operation. You have match, capture operations. You generate interrupts whenever there's a match, and then everybody knows what a state machine is. So a state machine is basically, you have you have states, and when you make a transition into another state, that is triggered by an input condition, and then an event will take place, and action will occur. So what we have done is, with the State Configurable Timer, basically we have taken a standard 32-bit timer, and we've added more logic to it. We've added the concept of state and event. So an SCT is basically, it can be configured as a 32-bit timer, or it can be configured as a 216-bit timer. And what you can do with the SCT is that once you're in a certain state, and when a certain input condition takes place, whether it's a match or whether it's a signal, falling, rising edge, you can actually generate an event. And once the event is generated, the event will trigger an action, and that could drive an output, or it can generate an interrupt, or it can halt the timer. And then once that is completed, you jump into another state. So what does all this mean? What does this mean? I'll go to a quick example. So if you wanted to generate a PWM with a dead time control, then you can use the SCT to do that. And this is a standard timer cannot do this. Basically, you can see here that there are two outputs in this example, and you can see that the first output goes low, and then there's a delay before the next output goes high. So you have a dead time insertion. You can also do a four-channel PWM with an abort. So you can actually have 4 PWM outputs, and let's say you want to trigger an abort in your application, where basically all the outputs go into their idle state, then you can do so with the SCT. You can basically have the abort as an input function to the SCT, and when that pin goes low, all of the outputs of the PWM are basically going to go to their idle state. There are 4 outputs on the SAT, yes, on this chip, yes. We also have a cookbook which we'll be releasing soon. It gives a bunch of examples with the SCT, and you can take these examples. You can actually see if it works for your application, or you can actually tweak it to meet your application requirements. At the end, the SCT can be used for PWM outputs, frequency detection. It can be used for lighting applications as well. And then we also have a graphical tool. So if you don't want to go into the details of the SCT, you can see here a quick example of here. You have 2 states running here, and depending upon the input condition, you jump from one state to the other, and you generate an action. So again, it's simplicity, right? We want you guys to be able to take this tool, Red State tool, which is part of our LPC Expresso, and actually what ends up happening is once you do this, you can actually generate a C code that you can copy over into your application, and you can use it with Kyle, IR, or Expresso. We also have a pattern match engine. I'll have to go a little bit quick now on this. Basically what we have here is that, what is a pattern match engine is basically that you can take 8 pins, and you can use it to create a Boolean expression, and you can replace any external glue logic on your application. So I'm going to have to skip through slides because unfortunately we ran out of time. But again, these slides are going to be available for everybody. And if you have any questions after the session, I'll be happy to help out in any way I can. So we have the USARTs, I2C. This is a quick demo that you'll see how the I2C wakes up from power down mode. Again, we can talk about this later. And then we already went over tools and support. So again, I just want to now just say, again, I'm hoping now everybody here has understood how easy it is to use the chip. Obviously, we'd have to look at it more, but again, just from the high-level perspective, you can see how easy it is to use this device. With regards to the tools, you've seen how the performance you can get out of this device at a very low price point. And then power saving, a lot of flexibility with the power modes. And code size, much smaller than the 8 and 16-bit family. Single cycle access. And again, the last thing I want to emphasize is easy to use peripherals. So this chip is meant for you guys to you can take it. I'm sure that you can replace your 8-bit parts with this part, and you can enhance your application with this part. So thank you very much.